Hi everybody, I'm just going to give you a quick explanation and rundown of what cure control is. We've developed the tobacco dryer controller and we've called it cure control. So I'm just going to give you some information around what it is and how it works. So the background is basically we wanted to have a fresh start. My brother-in-law contacted me and he said he wants to have a controller to manage the process, and he wants to start from scratch, not using something that was already in place. He was looking for a controller that could do slopes of temperature, and not staggered but actual slope. And then he had a discussion with some PLC suppliers, but it turned out to be very costly exercise to use PLC equipment for this purpose. As I said, it was very costly. And then open automation, or agri automation in this case, came into the picture. Right, so the solution that we built, new open source hardware and software, has made it possible to build integrated automation system at the fraction of the traditional cost, basically Internet of Things. We built the solution in 3 phases. Basically the R&D was in the first year. Then we developed test units, which was basically this last season, and now we've moved into the production of the units. So we looked at a lot of research that was done around curing tobacco, and there's a major myth in tobacco curing, is that you need to the human plays a very important role, that you need to add a pinch of this or a dash of that during the process to get to the correct curing of the tobacco, or the drying stages. But research has shown that if you can control the process, that you can get to the exact same results every time. It's like baking a cake. If you've got the recipe and you bake the cake using the same recipe every time, you're going to get the same results. Alright, so basically we use this as the input mechanism for driving the program that drives the controller. You are basically able to, as you can see here, here's a relative humidity slope, and then there's a temperature slope, and that's the basis of the controller. I'll show you how that works a little bit later, but we looked at this chart and decided to follow that same method in building the drying program. The user builds his own drying program, but we basically looked at this as a way of doing it. Right, so the first prototype we put together, and it had a remote web interface only, and we did a lot of logging, and we actually wanted to see what's going on inside the dryer, because it seems that people don't really know what's going on inside. So we decided to first log and see what was going on. So basically this is the dryer, the heat exchanger over here with a fan. It's got a flow damper. We positioned our probes in 4 places, as you can see here: T1 and humidity 1, T2 and humidity 2, 3 and 4, in different places in the dryer. Obviously this is a conventional dryer, so the fan will blow the air past the heat exchanger. It will go underneath the floorboards and then push it through the perforated floor, through the leaves, and then suck it in at the top again, and continues. If you open the vent at the back, it pushes out humid air in the front. So this is basically where we placed our probes. Here you can see where we had the probe, and it was the first test oven or dryer that we used. And this is the data we saw on a typical drying cycle with all our probes in different places. Now it looks very daunting, but it's actually, this is the humidity coming down and that's the temperature going up. And if you can recall that chart that I showed you early on, it basically looks the same. But bearing in mind, this drying process was done by hand. So if we look at these dips and all over the place. Right, so what did we see in the data? We saw major overshoots in temperature, and the temperature wasn't constant. You can see a dip here and then a major overshoot. We saw that the pressure and the airflow was not constant during the process. At some stage when the leaves dry, the hot air doesn't travel to the front of the dryer anymore. It will choose the path of least resistance and just cycle at the back of the dryer. Basically at this point here we can see that the one probe was cooler than that probe, and then it swapped around. That probe became hotter, and now this probe is the one at the back at the top. If we look at it, it's number 4. So the air at the back became hotter than the air in the front because the air took the path of least resistance. Right, so we've got now a new controller, and this is the controller that we built. It's got a touch screen, it's got full UPS capabilities, it's got a remote and local interface. With the touch screen, it's the local interface, and it's an IP65 cabinet, water and dust proof. We've made the cabinet white so that the sun doesn't play a major role with the electronics inside the cabinet. And this is where we've decided to place the probes. The temperature probe T1 and T2 is basically placed here, and then we've got one relative humidity probe over here. We open the damper all the way, and we use a VSD to control the speed of the fan. So basically, what did we see in the data? It will not be possible to reproduce 100% the same slopes by hand every time. If you see this relative humidity slope is all over the place. Now the next dry run to try and get that same slope will be impossible. So this is a slope done by hand, and this slope is what our controller produced. So the blue line is the target of the relative humidity, the orange line is the target of the temperature, and this red line is the actual temperature, and this green line is the actual humidity. So as you can see, the green line follows the blue line, and the red line follows the orange line. Over here at this point where we drop down, we discovered that at a certain point in time, when you are below 20% relative humidity, that's when you start drying the stokes. That's when you start ramping up to 74 degrees. It doesn't make sense to control the humidity anymore. Then we give it a static vent opening, and we let the humidity bleed out by itself. Because what will happen is, if you try and force this humidity down, you're just going to open the vent more and more and more, and you're going to waste a lot of coal, because you need to heat up the air a lot. So we gave it a static. You'll see in the control when I do a demo later, you can give it a static opening or let the controller control. We're able to see the actuator position over time as it opens and closes the vent to keep the humidity on target. We can see the speed of the VSD. Now we control the speed of the VSD, and we are able to ramp and slope, and also immediately move the speed of the VSD, as you can see, over a 7-day period. Alright, so we also discovered that you can use the data for fault finding as to what's wrong with your dryer. In this case, we had a dryer that did not want to stay on target. You can see here, this is the orange line, that's the target, and the red line is the actual temperature. So what would happen was it would be on target and then it would drop out, and it would be on target and it would drop out. So basically what we found was that one of the contactors only let 2 phases through, and the third phase basically failed, and this is the resulting chart. Once it was discovered and fixed, this was the result after that. So you can see the temperature staying on target. We also discovered that one of the dryers, there was air leaking in from the stoker fan, and it was blowing on the probes. This is the target line, and as you can see, once the line of the actual temperature drops below the target line, it will switch on the fan to basically push up the temperature, and then it will actually drop down and then eventually turn around and come up, and when it stopped, it overshot like almost 10 degrees, and then it will gradually come down. Now, after fixing the leak of air from the dryer, this is the actual slopes, and you only have an overshoot of 0.4 of a degree. We would also see temperature not being reached because of the coal creating a tunnel of coal that's dirty or wet. So this is basically what would happen. You would see this, the arches come down as it got less and less coal, and then at one stage it could not get onto temperature, and then the safety kicks in. It switches off the stoker, and then it lets you know that there's something wrong, and that's why you'll see this huge dip. But that's basically what happened. It would make this little hole in a tunnel, so it did not draw in the coal into the heat exchanger. We found that wet bulb stops working at 54 degrees, so controllers that work with wet bulb will not work past 54 degrees, and that's why here we had a wet bulb probe in there just to see our relative humidity still kept going fine probes, but at this point the wet bulb would break away and basically became the same temperature as the dry bulb. We can use the relative humidity control during the ordering / damping phase. So once the tobacco is dried, you need to put the humidity, the moisture back into the leaf so you can actually work with it. So here you can see opening the solenoid valve, the water will basically start blowing into the dryer, and the humidity will then start building up until it hits the target, and then the controller will make sure that it doesn't go over that target that you've set. That basically reduces mildew in the grading room. Alright, so some power saving that we saw by using the VSD. So the red is the actual usage of power during the drying cycle, and the green is basically the saving you're making during that cycle. So it's basically a 44.1% saving in electricity. Obviously this is South African Rand, based on the current Eskom tariffs. That's what you were saving per drying run, using the VSD with the controller that automatically sets the speed as and when required. Right, we're also experimenting with coal saving. We're busy controlling the duration of the stoker feeder by pulsing it on and off during a burn. Now this new season that's coming up now, we'll test this a lot more, but initial tests show that we can save between 25 and 45% in coal usage. We also going to offset the feeder with a fan, so that the fan will start blowing first for about 15 seconds, then the feeder will kick in 15 seconds later, pulse on and off, and then once on temperature the fan will switch off, but the feeder will still turn, pushing in coal into the fire. This will basically help to reduce back burning into the coal silo and to reduce damage to the tip of the feeder helix. Alright, so this is user interface. It's changed a bit since the slide was taken, but in the demo you'll see how it looks now. This is on the actual controller unit on the touchscreen. This is how you load a drying program. You do everything with up down arrows and buttons. So basically what will happen is you can create slots. Now a slot is basically a starting point of the temperature and an ending point, a starting relative humidity value and an ending point, a static value of the vent. So either you've got targets here or a static vent. So like here you've got no targets but the static vent set, or if you give it targets or the slope, the controller will basically do that. But if you give it a static value, it will basically then ignore those. You can then give it the start and end of the VSD. We've now added a coal percentage here, where you give it the percentage of coal you want during that slot and then the time. You can also save that program to a preset or load a preset. But basically these lines that you see here corresponds to a drying cycle like this. There's slot 1, which was an hour, slot 2, which was that whole period here. The temperature was ramping a little bit, but the humidity stayed constant. Then we dropped down the humidity drastically, started climbing with temperature, dropping the humidity down. When we got to slot 7, we had a static vent opening, climbing the temperature up to 74 degrees and then keeping it constant during the last phase. Right, this is the web interface of the controller, but during the demo I'll show you how that works. Here's the network architecture. Basically you've got your mobile devices and your laptops and everything like that on the internet, coming through the internet, then hitting a firewall, then your router, then we've got basically the server that holds all the backend information for your business intelligence. You have a switch with basically hooked up to all your access points. This is on your internal network, where you can then get to all the controllers that way. Right, so our support model is basically we give you spares on site. We are looking to bring in local agents in each area. It's a plug and play design, so it's fairly easy to replace something inside the controller. And then obviously remote support for us to dial in and or remote control the unit to see what is going on. Right, so what is the benefits of this solution? Well, obviously the solution cost, it's still expensive, but compared to other solutions it's cheap. And I think it will still reduce cost as we go forward. You get real-time alerting and monitoring. If something goes wrong, if a chain breaks, or if it can't get to temperature, it will send you an alert to say something is without, it's outside the parameters that was given, and then it will let you know. So basically what I'm saying there is that the first time this controller saves you a batch of tobacco, it's actually paid for itself. There's full history of telemetry data per run. Real-time data feeds, you can see what's going on remotely. You can access all the functions remotely, no matter where in the world. It's not difficult to operate. If you can work your cell phone, you can work this controller. Full user access control, who did what when. The solution is secure. We've got the full auto, where it will take control of the drying process based on the program that you've loaded, or you can just use it in manual mode. You'll produce better tobacco as the process is controlled 100%, and you'll produce the same tobacco every time. Reduce losses because of the alerting, as I stated there, by alerting and monitoring. You won't lose batches. You will reduce the losses because of the humidity control during the damping phase, so you get less mildew in the grading rooms or the classroom. Saving of coal and power during a run, and saving you time. You don't have to go to this thing every time to go and see what's going on. It will let you know. You can view remotely. In our second phase, we will be looking at business analysis services, business intelligence services. Yeah, that means what if scenarios. For argument's sake, you can ask the question, which dryer gave me the best results, what dryer used the least amount of power, which dryer used the least amount of coal, things like that. Right, so the roadmap forward, we're completing the user interface, user and web interfaces as we speak. Then we adding the cool down and damping phases as we speak, and then we're busy with the supply chain manufacturing setup, and then if there is a requirement, we'll build the whole monitoring backend for all the controllers. That basically includes the business intelligence part, and then obviously from that point onwards we'll be able to do bespoke integration, automation, and then consulting for whatever other automation you need. So we will be adding to our catalog. We are actually busy as we speak looking at the humidity control. We're building controller for 2 other farmers to maintain the relative humidity in the grading room, and then obviously greenhouse controllers and soil moisture monitoring and so forth. Right, so that's what the Cure control unit is about. I will then go over to a demo of how the software works.